Alright, so let's get started. In today's video, we're going to consider logistic regression. So in the previous videos, we started with introduction to machine learning, then we move on to what linear regression is. Now we're going to talk about what logistic regression is. Okay, so in this particular video, we're going to concern ourselves with what logistic regression is all about and why do we need a logistic regression if we have a linear regression. Okay, so we're going to get to understand the intuition behind logistic regression and what we use logistic regression for. In what situation are we going to need a logistic regression? Okay, so now if you see the simple definition that I've given over here, right? If you see this simple definition that I've provided here, now I'm saying that logistic regression, right? Logistic regression is nothing but we use it for predicting binary classes, right? So this is the key, right, for binary classes, right, or categorical variables. Okay, for binary classes or for categorical variables. So I'm going to show you what this means in a minute. Okay, so let me just move on to what we did last week and then get to find the difference between this logistic regression and difference between logistic regression and linear regression. Okay, so let's see what we have over here. Now for linear regression, if you remember the linear regression class, we were trying to predict the MPG, right? That's the miles per gallon, right? Miles per gallon of a car, right? We try to predict the miles per gallon of a car based on several other factors like the cylinder of the car, right? Like the cylinder of the car, okay, like the horsepower, right? Like the horsepower. So all these factors were helping us to predict this, right? Plus some other factors, right? The country that the car is actually originated from. Okay, so all these were helping us to predict this miles per gallon. Okay, that's what we did in the linear regression class, right? Trying to find a relationship between this output or this target variable and the other variables. Okay, that's what we did in the linear regression class. So if you have a problem where you need to predict a continuous output, right? Where you need to predict a continuous output. So what do I mean by a continuous output? Maybe you want to predict, say, the house price, right? The housing price. So in a particular city, right? Maybe let's say if we take, say, Mumbai or Delhi, for instance, maybe you want to predict the housing prices of the houses in there, right? So if you want to do something like that, then you can use a linear regression, right? In that case, the price might be maybe $2,000, right? Maybe it could be, say, $2,000, right? Something like that. It could be, say, $2,000, or it could be something like 15, right? 15.5, right? 15.5 $1,000, right? Something like that, right? 1,500, something like that, dollars, something like that. Okay, or it could be maybe 20,000, maybe 20.7, right? 0.7 thousand, right? Something like that. All right, like that. Okay, so the price could be in this form, right? It could be a continuous form, right? That's what you try to predict, right? Just like the miles per gallon in this case. Okay, so if you try to predict something like that, then you need linear regression to actually do such kind of a problem. Okay, for instance, the stock price. For instance, the stock price could be maybe 54 point, right? It could be, say, 54.72, right? It could be something like that, right? That's the stock price. It could be something like that, $54.72. It could be something like that. So when you are predicting something like this, then you will need linear regression to do. You need linear regression to do such problems. Okay, and don't forget, whatever we are doing now, we have a target, right? You have a target, right, variable that we are trying to predict. So we are dealing with supervised machine learning, right? So whatever we've been talking about so far, we are dealing with supervised machine learning problem. Okay, we will talk about unsupervised machine learning problem also in a different class. Okay, so today what we are going to concern ourselves with is logistic regression. So why, if linear regression can help us to do all these, right, why do we still need logistic regression, right? So you might have a situation where you need to actually predict the constant output, right? You need to predict a constant output or a categorical output, right? For example, if you take, say, whether a patient can have cancer or not, right? Whether a patient will have cancer or not, or whether a customer will churn or not, right? So in that case, you see that we have fit in two ways. So we are basically doing something like whether the person will buy, the person will subscribe to a loan or not, right? So a yes or no, right? Something like that. Okay. So if you have such problem, then you need a logistic regression to deal with that. Okay. As we progress in this tutorial, we're actually going to see some of the shortfalls of linear regression and why logistic regression comes in handy, and why most of the time we will be using logistic regression in most of the cases. Okay. So we are actually going to see that, okay, maybe you want to classify whether an email is spam or not, right? Then logistic regression is going to come in handy, okay? And we're going to see more of this as we progress in the course, all right? Also, don't forget, although we have the name to be logistic regression, right? But basically we use it for classification problem, right? Like for instance, yes or no, right? It's a classification problem. Whether a patient is having cancer or not is a classification problem. We are classifying the patients into cancer patients or not a cancer patient, right? Or whether the person will churn or not churn, right? Whether a customer will buy an insurance or not buy an insurance, right? Whether an email is a spam or not a spam. So in that case, it's a classification problem. We are classifying into two categories. Okay, that's what we are doing. Right? It could not necessarily be two, it could be more than two, right? But in this example that I'm giving here, it's just in two categories. Okay, so in that case, right, it's just a classification problem, although the name is a logistic regression, but basically we use it for classification problem. Okay, now let's go to the Jupyter notebook over here and then see an example, right? That's going to actually make things more intuitive for you to understand. Okay. So as I said, this course is practical, so we try to make everything more practical for you to get to understand the intuition behind every concept that we talk about. Okay, now if you see what I have over here, right now, what I'm doing over here, if you remember the NumPy class, we learned how to create a list. So the same thing that I'm doing over here, right? Nothing different. I'm creating a list, right? I'm creating a list here. If you can see that I'm using my square bracket, then with some numbers in there, right? Some float numbers in there, right? Some ints, of course. And these are nothing but number of hours that a student will study, right? And then whether the person will pass or not. Okay, so that's what I'm doing over here. So this one represents a number of hours that the student will study. So someone study for say half an hour, someone study for say 75 minutes, right? Someone study for say 1 hour, one and quarter, right? And then 1.5, something like that. Okay. So all these are represent hours that people will study, right? Number of hours that people will study, and then this is whether the person will pass or not, right? So if the person will pass, we represent whether the person will pass. So if the person pass, we represent that with 1. If the person will fail, right? If the person fails, we represent that with 0. Okay, so in this case, we can see that we have two categories here, right? Whether pass or fail. Okay, we have pass or fail over here. So this is what we are going to use to actually understand the intuition behind logistic regression. Okay, so whatever I'm doing here is something that we are familiar with. Converting all the list that I have here into a series, right? So that's why I'm using pd.series so here to convert everything, right, to series. And then this is a number of hours, converting it to series, whether the person will pass or not. I'm converting that one to series. Then after that, I put everything together. Remember, if I convert it to series, I store it in a variable called HRS, or just hours. And then if I convert the pass, whether the person will pass or not, I store everything into PF, right? So after that, I concat everything. That is, I put everything together over here. Then I store it in what is called a variable called data. Okay, I'm using axis equals 1 to indicate that I want to just concat them column wise, right? I want to concat them column wise. Okay, now after that is done, if we come down here, right, what I'm doing is that I'm just converting this. So I concated this series, right? We have HRS and then PF, right, whether the person will pass or fail, and then this HRS here, right, which is the number of hours the person studies. Okay, now after I put everything together, right, I'm going to convert everything here into a data frame, right? I'm going to convert everything over here into a data frame. So that's what I'm doing here, pd.dataframe, right? So if I do that, right, I will be ending up with, remember that when we put them together, we have this 0, 1. So I want to just rename this 0 and then the 1, right? So this 0 column represents number of hours, and this 1 column represents represent the whether the person passes or fail, right? So that's what I'm going to do. So the 0, I'm going to rename the 0 to HRS, which is hours, right? And then the 1 to whether the person pass or fail, right? And I'm going to use in place equals true, so that whatever changes that I'm doing will actually reflect in the original data set. Okay, now if I convert this to a data frame, I store it in a new variable called df. So in df, that's what I'm doing over here. So you can see the df.rename, and I'm renaming this, right? So I'm selecting the columns, so column 0 to be renamed as HRS, right? So this column 0, right, to be renamed as HRS, and this column 1 to be renamed as P/F, right? That's what I'm doing over here. So if you can see the new one that we have here, we have HRS, and then we have P/F. Okay, so now we can actually see the number of hours, and then we can actually see whether the person passes or fails. So we can actually see this in the form in a tabular form, right, in a pandas data frame, right? So that's what is basically happening over here. Now, if we take a look at this, right, you can see that someone studied for 50 minutes, the person failed. Someone studied for 75 minutes, the person failed. Someone studied for 1 hour, the person failed. Someone studied for 1.5 hours. 1 hour 25 minutes, the person failed. Someone studied for 1 hour 50 minutes, the person failed. Someone studied for 1 hour 75 minutes, the person failed. Someone studied for, so all these are those who failed, right? All these are those who failed. Someone studied for 1 hour 75 minutes, the person passed. Someone studied for 2 hours, the person failed. Someone studied for 2 hours 25 minutes, the person passed. Someone studied for 2 hours 50 minutes, the person failed. Someone studied for 2 hours 75 minutes, the person passed, right? So if you go all the way down, someone studied for 4 hours, the person passed. If someone studied for 4 hours 25 minutes, the person passed. 4 hours 50 minutes, 4 hours 75 minutes, 5 hours, right? All these people pass, right? So we can actually conclude that the longer hours the person sits down and then study, right, the person is likely to pass, right? The person is likely to pass, right? But if the person studied for less hours, the person is likely to fail, right? We can make that conclusion over here, right? That those who study longer hours are likely to pass, but those who study less hours are likely to fail, right? Although there are some anomalies where someone even studied for 3 hours 50 minutes, but the person still failed, right? And someone also studied for 1 hour 75 minutes, but still the person passed. Okay, so there are some anomalies in here, right? It could happen due to certain circumstances. Maybe this person is sharp, right? Maybe the mind itself is quite sharp, or maybe the person actually has seen the question paper before, so the person did not worry himself spending a lot of time studying, okay, and the person passed. And maybe this one, something happened on the day that the exam took place, right? So a lot of circumstances could account for why someone will study long hours and then the person will fail, right? And then maybe the person's even studied for long hours, but he did not even understand what he studied. Okay, so a lot of factors could actually account for this, right? And all these are just anomalies that might happen, but generally you can see that as people study more hours, right, they pass, and as they study less hours, they fail, right? So we can actually make this kind of conclusion from here. Okay, now let's move one more step and then plot this using the scatter plot, right? Let's plot this using the scatter plot. Okay, so what I'm doing over here, right? What I'm doing over here is that I'm setting the figure size, right? That is I'm using the PLT, which is matplotlib, right? Which is matplotlib, and then I'm using .figure, and I'm setting the figure size to be 15 by 10, right? That is the length now here, right? If I show you this, so the 15 is nothing but the length now here, okay? That's the 15, and then the height over here, right? The height over here will be 10, okay? So that's basically what I'm setting over here, which is 15, 10. So I will have my 15 here, 15 unit here, then I'll have my 10 here. Okay, so that's basically what is here. Now I'm using SNS, which is the seaborn, right? And I'm using scatterplot. And in scatterplot, I am plotting the hours and then whether the person pass or fail, right? And my data is stored in DF. Okay, so that's what I'm specifying over here. Now you can see that I have my whether the person will pass or fail. Remember that we have only 0 and then 1, right? That's why you see our data point being here, only at this part. And then we have it somewhere here, right? Only at this part. So at 0, right? Either at 1 or at 0. That's what is actually happening here. That's why you don't have anything in between here. Well, it's either the person will pass, that is 1, or the person will fail, right? That is 0. Okay, that's what we have here. Now, as we plotted this, right? As we plotted this, now we can actually fit a regression line, right? Just like we did. I mean, a linear regression line, just like we did in the previous video. Okay, we can actually in the linear regression class, we can fit a line over here. Maybe we can do something like this, right? Fit a linear regression line, something like that. All right. Now, if we try to fit this linear regression line, don't forget equation of a line is something like y equals. We actually talked about this in the linear regression class, right? Something like that. Okay, so now that's this line that we have over here. Now, this is the data point that we have, right? That whether a person will pass or not, right? Whether a student will pass or not. So this is what we have. If a new data point comes in, right? If a new data point comes in, so let's say a new student comes in, and then we see the number of hours that the person has studied, right? So over here, maybe the person studied for, say, 1.5 hour, right? Or maybe the person studied for 1.5 hour, right? Now we can actually predict whether the person will pass or fail. Okay, so now if we trace this to our regression line here, that's our linear regression line, and then go this way, maybe our prediction will be something like so in between the 1 and then the 0, think of it as a probability, right? A probability of whether the person will pass or fail. Okay, now if we trace it to this part, we can see that maybe 0.0, right? Maybe 0.0, or maybe yeah, in between this will be something like this. Let me clean this. Remember, we have 0, then we have 0.2, 0.4. So in between this could be maybe 0.1, right? Okay, in between this could be, say, 0.1. All right, it could be 0.1 over here. So we can say that this person will fail, right? This person will fail. We will associate that person to 0, right? Because 0.1 is actually closer to 0 than 1. So we will conclude that this new student who is studying for I mean this number of hours, which is 1.5 hour, will fail. However, if another student comes, right? If another student comes and that student studies for, say, 3.5 hours, right? If that student studies for 3.5 hours, then we can actually predict that. We can actually predict, right, by tracing it to our regression line over here, right? We can actually predict, right, maybe something like this, right? Maybe 0.661 or something like that. Okay, now if we take 0.61, right, if we take 0.61, we can see that this 0.61 is closer to 1. Okay, so we can conclude that this student who is studying for a student who is studying for 3.5 hours, so actually now we can actually conclude that this student will pass, right, based on the probability that we are able to achieve, which is closer to 1 than 0. Okay, but this one studied for 1.5 hours, and we can say that this student will actually fail. Okay, so that's basically what is happening over here. If we fit a linear regression line over here, right, that's basically what is going to happen here. All right, so now this is actually working for us perfectly, right? We've been able to fit a linear regression line, and also we've been able to fit a linear regression line, and besides we've been able to make predictions for new students that will come in. Okay, so now even if we want to generalize, we can say that any student whose probability, right, so if we take here to be 0.5, right, we can say that any student whose probability will be above 0.5, right, we can say that that student will pass, right? That student will pass. However, if any student comes in, we trace the person's probability and is below 0.5, right, we can say that that student will fail. Okay, so we can make that generalization that any probability that will come in which is greater than 0.5, right, which is greater than 0.5, we associate the person to say pass. But if any probability comes in and the probability is less than 0.5, right, then we associate that probability to say fail. All right, so we can actually make that generalization over here. Okay, now this is working for us perfectly. Okay, this is working for us perfectly. Now, if we think about it carefully, if we think about this carefully, right, we can still figure out some problems with this. Okay, we can still figure out some problems with this. Now, what are some of the problems that you can actually see? Just think about it and see if you can actually identify any problem before I talk about it. Can you actually identify any problem? Okay, now I am sure you might have identified some of the problems. Okay, now what do we want, right? What we want to do over here is that whether the person will pass, that is 1. Okay, let me change this pen actually. Okay, now whether the person will pass, let me actually clean this board. Okay, whether the person will pass, that is 1, right, or the person will fail. Okay, so whether the person will pass, that is 1, or the person will fail. So if we fit the regression line, right, if we are saying that we are fitting a regression line like that, okay, all right, if we fit a regression line like this, right, now you can see that this regression line doesn't actually capture the data points. See where some of the data points are, right? Even if you see this one, see where some of the data points are. It doesn't actually capture the data points as we want it to capture. Right, so if we are fitting a regression line, what we want is that the regression line, right, that particular regression line should be able to capture as many data points as possible, right? Most of the data points should lie closer to this regression line. That's what we want, not a regression line where the points are lying further away. Remember that we talk about the mean square error, right? The mean square error. So if we want to measure the error of each of the data points that we have over here with respect to the regression line, you can find out that this will end up having a huge error over here, right? We'll end up having a huge error if the points are lying very far away from the regression line. So what we want is and I mean the distance between each point and the regression line represents the error that we are making, right? That represents the error that we are making, and we don't want to make any huge error, right? The error that we want to, we want to minimize the error. That's why we use these measurement of error to actually measure how well we are doing. Okay, so we want to minimize the error by making sure that these points lie closer to the regression line that we are dealing with. Okay, we want to make sure that all our points are lying closer, or if possible on the regression line. Okay, but if you see what we have here, you can see that most of the data points are lying far away from the regression line. Okay, that's one of the problems. Now if we say that we have either the person will pass or the person will fail, that is 1 and then 0. Okay, so whatever we have, even if we want to consider the probabilities, right, even if we want to consider the probabilities, those probabilities are supposed to lie between 0 and then 1, right? They are supposed to lie between 0 and 1, so we cannot go beyond 0. But if we extend this, this regression line that we fit here, we might end up having, say, maybe this one will also continue. We might end up having, say, 2. We might end up having, say, 3. We cannot have a probability more than 1. We cannot have a probability less than 0. Right? We cannot do that. We don't actually want to go to that extent. Okay, we don't want to go to that extent. So we want everything to be between 0 and then 1. But if we continue this, right, if we extend this line, then it means that that won't work for us in this situation. Right, linear regression won't work for us. If we plot a linear regression line like this, it won't work for us. Okay, so that's another shortcoming that we can think of. Another thing that we can also think of, right? Another thing that we can think of, apart from the points being lying further away from the line, and also if we extend, we will end up having values greater than the distance that we want to measure, right? That is between 0 and then 1, right? We don't want to go beyond that, but if we extend this line to go beyond that. So apart from these two problems, another one that we can think of is, let's say a student, right? Students who studied for 2 hours, right? This person failed. This person studied for 2 hours and the person failed. Okay, now if this person studied for 2.5 hours, right? If this person studied for 2.5 hours, if we trace this, right? If we trace this and then trace it over here, right? It's a bit squeaky, but just forgive me. Okay, if we trace it over here, right, maybe we might end up at 0.5 or maybe 0.523, something like that, maybe 0.52, something like that. Now, these students just increasing from 2 to 2.5, we've not even go to 3 hours, right? Just increasing it by only about half an hour, right? The person is able to pass, right? The person is able to pass. However, if we increase the number of hours of this person, right? This person is already passing, right? This person is already passing. If you trace the probability of whether this person will pass or not, is even greater than 0.8, which is more closer to 1, right? So this person has already passed. So if this person increased the number of hours to say 4.5, right? Still, the person is still in the passing zone, right? So what is the significance of this person increasing the probability? It doesn't make any difference anymore. But this person, if this person that has failed increase his probability from his number of hours from say 2 hours to 2.5 hours, this person pass, right? This person gets to pass, and that's a significant results, right? That's a significant results because the person was failing and now the person is passed, and that's a significant significant result. But if the person is passing already and the person increased the number of hours and the person is still passing, I mean, we don't actually realize the significance of this number of hours that the person is actually doing, right? We don't actually recognize the extra hours that person put in. But if we see this one, right, the person increasing it by just half an hour, the person is able to pass, and we can recognize that this 0.5 over here, right, that is the half an hour the person increase. It's a very significant, I mean, hours that the person has put in, right, unlike this one. So there's a little bit bias here, and we can actually I mean, think of it as we want to take the situation in this manner, right? We need to actually do something about this, right? Regarding the fact that if we extend this line, we will go beyond 1. If we extend it here, we go beyond 0. And some of the points also not lying on the regression line, right? Not lying on the linear regression. So all these are some of the limitations, right? All these are some of the limitations of this all these are some of the limitations of this linear regression, right? All these are some of the limitations of the linear regression, which is making it unsuitable when it comes to this kind of classification problems, right? When it comes to this kind of categorical classification problems, okay? So what we can do over here, right? What we can do over here is to actually try and then capture as much data points as possible, right? To capture as much data points as possible. So what can we do over here? If we see this, right, let's try, and maybe let me use the different color over here. Okay, so maybe this one will do for us. The points are already blue, so maybe I will try to use something like this. Okay, now if we try to capture these points, right, let's try and then maybe capture these points. All these are normally points, so let's try and leave that and then capture these points, right? Let's try and then capture as many data points over here as possible. Okay, now can we now connect these two, right? If we are able to do this, right? If we're able to capture as much data points as possible, right? Can we now connect something like this? Can we now do something like that? Okay, now if you see this curve, right, this curve, although it doesn't capture all the data points, right, it doesn't capture all the data points, right, all the anomaly data points over here, but you can see that most of the data points that are more significant, right, whether the person studied for low hours and the person will fail, or the person studied for high hours, right, don't forget these are hours, so the higher the person studied, the person gets to pass, that is, the person gets to lie under 1. If the person studied for low hours, the person gets to fail, that is lying somewhere here. Okay, so you can see that this line or this curve actually captures most of the points, right? This curve actually captures most of the points for us. All right, this curve actually captures most of the points for us. Now, a curve like this, right? A curve like this that looks like S, right? That looks like not a perfect S, but it could be a stretch S, something like that, right? A curve like this that looks like an S shape, right? Is what we refer to as what sigmoid curve. Right, it's what we refer to as the sigmoid curve. Okay, it's what we refer to as the sigmoid curve, and you will encounter this sigmoid curve over and over again as we progress in this course. Okay, you're going to encounter this over and over again as we progress in this course. All right, so we have several ways of plotting this sigmoid curve. Right, we have several ways of plotting this sigmoid curve, and I'm going to show you some of them. Okay, so one of the ways that we can actually plot the sigmoid curve, right? So let me actually get rid of. Okay, let me leave this one and then I'll do it again over here. Or probably let's go here, right? So let me come here and then I'll actually do it from here for you to actually get it. Okay, so we have this. Let me actually get it from here. Okay, so we're having that something like this. Okay, so this is something that we've been dealing with so far. Okay, that's what I'm going to do. So we have our 0 here. We have our 0 here, which represents those who will fail. We have our 1 here, which represents those who will pass, right? Then we have some 1, 2, 3, right? We have some 4, we have some 5, right? We have some 6 over here. Okay, then we have some data points that we're lying here. Let me change this color. Okay, we're having some data points, right? those who study for less hours and they get to fail, right? So with some anomalies, right? With some anomalies lying somewhere here. And then we have those who study for long hours, right? Those who study for long hours, maybe 5 hours and 6 hours, something like that, right? That they got to, all right, that they got to pass, right? Those who study for long hours, and then they got to pass. Irrespective of that, there were some anomalies also in, right? Those who study for less hours, but they still pass. Okay, so this is what earlier on we were dealing with, all right? This is what we were dealing with. So let me actually let me actually try and then fit this line. So this is what we actually try to capture. We capture this, right? And then we try to plot this smooth, right? This smooth curve that looks like S, right? And don't forget that we say that a curve like this is what we refer to as the sigmoid, right? As the sigmoid curve. Okay, a curve like this is what we refer to as a sigmoid curve. And as I said, there are several ways of plotting the sigmoid curve. So just think about the normal distribution, right? So if you pick, let me actually use this. Okay, so if you take the normal distribution, right? If we take the normal distribution actually looks like this, right? It actually looks like this. Okay, then it will go like that. Okay, then maybe something like this. I'm just plotting the other half as dots, right? So if you think of the normal distribution like this, right? Normally it's like this, right? It's just like that. Okay, so the other half here is what I've plotted with dots. Okay, just like what I have here. Now, what is actually happening here is that if we take the normal distribution, we can use this normal distribution to plot this sigmoid curve that we have over here, right? Think of the sigmoid curve as more like this, right? Going that way, right? So if we're having the opportunity to come down like that, then it's going to be looking like the sigmoid curve, right? It's going to be, looking like the normal distribution if we are supposed to go this way. But if you see this one looks more like the half of a normal distribution. Okay, so if I clean this part, right, if I take this part off, right, you can see that now we have something that looks like the the sigmoid curve, just like we're having here. Okay, just like we're having here. Now we have something that looks more like the sigmoid curve. Okay, we have something that looks, so we can actually use that, right? We can actually use the what is called the normal distribution, right? You can use the normal distribution to actually do that. Okay, we can use the normal distribution to also plot that. And there's another one called the probit, right? The probit regression, right? Let me write it here for you to see. We have what is called the probit, right? The probit regression, which we can also use to plot the same sigmoid curve, right? And the formula for that one looks something like this. We have some y, right? We have some y equals something like this, right? Something like that. And then you have your x over here. Okay, this symbol that I'm giving here is nothing but it's nothing but the cumulative, right? It's just the cumulative distribution of the normal distribution, right? So if you think of the normal distribution over here, right, remember that we put this point over here, right? So cumulatively, as we add all of them together cumulatively to that point, right, that's what this symbol over here is going to do for us. So this one is nothing but the cumulative, right? The cumulative distribution, right, of the normal distribution. Okay, of the normal distribution. So that's what this symbol over here represent. Okay, so this is basically what is referred to as the probit, right? What we are actually going to use, right? What we are actually going to use over here is what is called the logit, right? It's what is called the logit function. Okay, we're going to use the logit function, and the logit function actually looks like this. It looks something like this: 1/1 plus e exponent negative of a plus bx. Okay, it looks like this. This basically what we'll be using throughout our machine learning class, and even if we progress to the deep learning class, we're still going to encounter this over and over again. Okay, so we're going to actually consider this logit function, basically because this one actually helps us to be able to plot this sigmoid curve as easier as possible. Okay, so we're going to actually consider that. Now let's take a critical look at this Logit formula that I've put here. Okay, let's take a critical look at this Logit formula that I've put here. Right, this is just a bracket. Right, this is just a bracket, and then we have another bracket here. Inside the bracket is what we have a plus bx. Okay, so if we take a critical look at this, right, this what we have in the bracket over here, right, it's nothing but the equation of the line, right? So if we pick equation of the line, we say that we have mx plus c, right? So it's just the same thing. You can think of this m as the b over here. You can think of this x as this x. You can think of this a as this. Okay, so it's just the same thing, right? So most people will also write equation of a line as bx plus c, right, or c plus bx, right? So it's all the same thing, right? It's all the same thing. So this is more like the equation of the line, okay? And our x here, in this case, our x here is the number of hours that the person will study. Okay, our x here is more like the number of hours that the person will study. So this x will actually help us if we're able to determine the best b and the best a. We will be able to find, we will be able to predict whether the person will pass, which is y, right? Whether the person will pass or not. Okay, we'll be able to do that. Now, after we've been able to identify this, what we can actually see over here is that this x or whatever we have over here, right, could range from negative infinity to positive infinity, right? Whatever value that we are going to have up here is going to range from negative infinity to positive infinity. All right, it's going to range from that range. Now, if that is the case, right? If that is the case, it means that the whole of this, right? The whole of the whole of this exponent here is going to be negative infinity plus positive infinity, and this e is going to be exponent of that. Okay, so what I'm saying is that if this one, if what we have here is going to be either negative infinity or positive infinity, then we're going to have something like 1 over 1 plus e negative plus or minus, right, plus or minus infinity. Okay, so it's either the whole of this is going to be negative infinity or positive infinity. Okay, so we're going to have something like this. Now, if e, right, if e exponent, if we pick e exponent positive infinity, right, if e is equal to positive infinity, then what we are going to actually have is actually approximating to infinity, right? However, if we have e exponent negative infinity, then we are going to be approximating to 0, right? You can actually check this from your scientific calculator and then see the solution for this. Okay, now what is actually happening over here is that if we have this, right, if we have this to be either positive infinity or 0, right, then what is happening is that we can have 1 over 1 plus, so if e is if we pick e equals negative infinity, right, if we pick the negative part, then we are going to have 1 over 1 plus, we remember that we say that e exponent negative infinity equals 0, so we will be having 0 over here. We're going to have 1 over 1, which is equal to 1. Okay, and if we pick the positive part, let's say 1 over 1 plus e exponent, say positive infinity, right? Remember that we say that positive, if we pick the positive part, e exponent positive infinity is going to give us infinity. So we're going to have 1 over 1 plus infinity, right? 1 plus infinity over here. And 1 plus infinity is still going to be a very large number, which is still going to convert to infinity. So we're still going to have 1 over infinity, right? And 1 over infinity, since we are dividing this, right? Since we are dividing something over the infinity, is still going to converge to 0. All right, this thing is still going to converge to 0. So now what is happening here is that we'll be able to bring all the values that we have between 0 and then 1, right? Between 0 and then 1, right? Between 0 and 1. Then that is what makes this Logit function more useful, right? That's what makes this Logit function more useful in production, right? That's what most people will try to use, because it will help you to make all your values, right? All your values lie between maybe let's represent your values with n, right? It will make it either greater than 0 or less than 1. Okay, so it's actually going to lie between 0 and 1. Okay, so that's basically why the Logit function is more useful, right, in production. Okay, and more intuitive if you think about it. Okay, one more thing before we move from here. One more thing. People also, you might end up seeing this kind of equation, right? People also try to relate this logistic function with or logistic regression or function, right, with the linear regression. Okay, and that's why mostly we actually can say that logistic regression approximates to linear regression. Okay, now if you pick this, right, if we say log, right, whether the person will pass will be y, right, and whether the person will not pass will be 1 minus y. Okay, if we pick this, right, let me actually do it this way. Okay, the more reason why people actually say that a logistic regression can approximate to say linear regression. Okay, so if we pick the probability that the person will pass divided by the probability that the person will not pass, which is 1 minus y, all right, and then we find the log of that. If we find the log of this, right, we can actually say that this is actually equal to the normal the linear equation that we have, right? This is linear. What we're saying is that if we find the probability that the person will pass, right, and the probability that the person will not pass, and then we find the log of that, this is actually going to give us a linear. All right, so let me show you what that means, right? What that means. Now think about this equation that we have, here, right? It's approximately, right, it's this the same thing as the Logit function, which is nothing but 1 over there's no negative there, so don't think about this, just this one is not there. Okay, so it's just 1 over 1 plus e and then negative a plus bx. Right, so you can see that we have the linear over there. Right, so what we say that these two equations are equal, right? These two equations, right? So if I do this, right, we say that these two equations are equal. Okay, now let me show you why we say that these two equations are equal. If we pick this, right, if we pick this over here, which is log the probability that the person will pass divided by the probability that the person will not pass, that is log of that equals a plus b, right, equals a plus b x. Okay, something like that. Now let's take this log, right, to this side. If we do that, we are going to be left with y divided by 1 over y, right, equals, now if you find the log of this side, it's actually going to give you e exponent a plus bx. Right, that's what is actually going to happen. Now, let's try and then flip this equation. Remember, if we have say a, right? We can say that a is over 1, right? And then any whole number is over 1, right? If we pick say 100, we can say that 100 is over 1. The same way. So if we want to flip a, right? If we want to flip a, then a is actually going to be like 1 over a. Right? If we want to flip 100, it's actually going to be 1 over 100. Right, I mean like 10 it over, right, if we want to do it that way. So let's try and flip this one. If we try to flip this one, then 1 minus y will actually go up and then the y will come down, right? So this one will go up, this one will come down. Basically, that's what is happening over here. In the same way, we can see that the whole of this is over 1. Okay, so if we flip it, then we're going to have 1 over, right, 1 over e exponent a plus bx. Okay, we're actually going to have something like this. And don't forget, right, if we have 1 over a, it is the same as a negative 1. Okay, so if we have say 200, right, 1 over 200 is this the same thing as 200 exponent negative 1. Okay, so this particular thing over here, right, can be written as e exponent negative a plus bx, right? We can actually write it in that way. And then if this one, let's just maintain this one, 1 over y. 1 minus y divided by y. Okay, so I just copied this one here, right, without changing anything. And then this one, right, I just rewrite this one as this. Okay, remember what I told you over here, so I just did that over here. Now 1 minus y divided by y, right, they all have common denominator. I can separate this denominator, so I can write it as this 1 over y minus y over y. Okay, I can separate this one that way. Okay, and then let me just maintain this part. All right, a plus bx. Okay, let me maintain this part. Now if we do this, right, we can see that y over y is actually going to give us 1. Okay, so if we write it again, we're going to have 1 over y minus 1 equals this e negative here, right, so a plus bx, right, we're going to have something like this. Now let's try and then take this minus 1 to that side. Okay, Now what is going to happen is that if we are going to have something like this, right? 1 plus, remember, if we take a negative here is to this side, it's actually going to be positive. Okay, it's actually going to be positive. Then this one over here is already positive, right? Remember that it is exponent negative, but the whole function here is positive. Okay, so we have plus our e, then exponent negative a plus bx. Okay, now you see what we have over here. Now the same way that we flipped this one, right? The same way that we flipped this one, let's try and then flip this one again. Now if we flip this one, it means that our y is going to go up, our 1 is going to go down, right? Remember that I say that if we have a whole number like say, or any letter, right, we're going to have a. If we have a here, we can say that a is over 1. If we have say 200, right, we can say that 200 is over 1. Okay, and normally we just write it as 200. We don't actually bring over 1. We don't do that. We just write it 200. So if we flip this one, ideally y is supposed to be over 1. Okay, but we can just write it as y without the over 1. Okay, so we can say that y equals, and then the whole of this, right? If we flip the whole of this, right, don't forget the whole of this will be over 1. Okay, so if we flip this one, then let me actually bring this a little bit down. Right, let me bring this one a little bit down. So this one is actually giving us y over here. So if we flip this one, then we're going to get 1 over 1 plus e negative a plus bx. Okay, now you can see that we have our Logit function. Right, so we got our Logit function. I mean, from this, right, we got our Logit function from this. Remember that earlier on, that's the function that we introduced it, and we're seeing that is just, I mean, it can be approximated to linear function, right? It's just linear. The Logit function is just linear. So if you pick the log of this, right, it's linear, right? And if you actually try to work it out, you're actually going to end up having this, just like we just did, right? Just like we just did over here. Okay, so basically that is the intuition behind that, right? Basically that's the intuition behind logistic regression, right? You might have a situation where you need to actually capture some data points, right? And you're going to need a sigmoid curve, right? You're going to need a sigmoid curve to actually do that, right? And we use this Logit function mostly, right? We use this Logit function mostly to actually plot this this sigmoid curve, right? We're going to use this Logit function to mostly plot this sigmoid curve to actually find a relationship between, or maybe classify, right? So in this case, classify whether a student will pass or a student will fail. Okay, so in this case, if a new student comes, right, if we see what we plot here, right, if we use this and a new student comes and that student studied for less hours, right, we are likely to predict that that person will actually fail, right? It will lie on the line straight away. And if the person studied for long hours and we trace it to our sigmoid curve, we can actually see that it's actually 1, right? The person will actually pass. Even if the person comes and the person studied for 3.5 hours, right, we can still trace over here and then see that the person will still pass. Okay, so the sigmoid curve actually help us to actually make better prediction as compared to if we are to use a linear regression for this kind of a problem. Okay, so in the next video, we're actually going to talk about how we can find the best sigmoid curve, right, and minimize our error. Don't forget that in this case, right, there could be several sigmoid curves that we can draw, right? Maybe one could go this way, right? So one could go that way. One could capture it in that way. Something, it will not go beyond that. So this one will not. So something like that. Okay, so there will be several sigmoid curves that we can actually draw. But how do we find the best sigmoid curve? Just like if we are drawing the linear regression line, how do we find the best linear regression line? How do we find the best fit, right? How do we find the best fit line? Just the same way, how do we get the best sigmoid curve? So that's what we will discuss in the next video. Okay, so see you in the next video.